Hello, Mrs. Plenda back again, and we're going to talk today about equations that end up having special solutions. This means they don't have a single answer, they might have no answer or infinite answers. So let's go ahead and take a look at what these kinds of equations look like. First, let's remember what equations look like when we have variables on both sides of the equals, because they're these types of problems that might have a special solution. Now, one thing that we notice is that we have to figure out a method that's going to move our variables all to one side of the equals so that we can go ahead and solve these. But mostly we're going to be using our usual solving techniques. So taking a look at this, the first thing I want to do is simplify, just like in my multi-steps. So I'm going to take this -2 and distribute it into the parentheses to make the parentheses go away. That will give me -12. Negative times a positive gives me -16m plus 3 is equal to 36 minus 7m. That all stays the same. Then I want to combine my like terms. I see I have -12 plus 3. That's going to give me -9. And the rest of the problem stays the same, so I'm just rewriting it so I don't forget any parts. Now I want to make sure that my variables are all going to move to one side of the equal so that I can continue solving this. We usually want to move the one that is smaller. So since -16 is smaller than -7, that's the one that I'm going to move. And what this usually does is it means that we're going to deal with positive variables instead of negative variables. So you don't have to add the 16. You could add the 7 instead and still get to the answer just fine. So now I have -m equals 36. -7 plus 6 gives me 9. We go. So now, since I moved all my variables to the right, I have to move all my numbers to the left. So I will subtract the 36. And now I have -45 is equal to 9m. So I'm going to go ahead and rewrite over here so I have space to do some more work. My last step is to go ahead and divide by 9. And I end up with -5 is equal to m. So the big difference for these problems is making sure we're able to move those variables across the equals by adding or subtracting. And in this case, we went ahead and added the 16. Okay, so that was our new step that we talked about for when we have variables on both sides. But we can also have a couple of very special situations that happen when we have variables on both sides of your equals, and I want to talk about those real quick. So our equations actually have 3 different ways that they can work out. So I want to go ahead and talk about those now. Now our first one we're going to talk about is the one that we're used to seeing, where in this case the box is representing x. We don't know what's in it. So if I were to write an equation for this, I end up with 4x equals 2x plus 6. This is our usual sort of equation. They're the kinds that we've been practicing. I could go ahead and solve this. So if I went and solved it, I would move all the variables to one side of the equals. So I would subtract the 2x as the smaller one to the other side of the equals, moving them over to the left side. That would give me 2x is equal to 6. I would go ahead and divide the 2x as my next inverse step, or sorry, just the 2, the x stays put. And I end up with x is equal to 3. Okay, this is the type of problem that we've been solving, and it's our usual type of problem. There's only one value that is going to make this balance out at the end. X is equal to 3 and no other number. There's just one answer. So this is our usual type of equation. But there are actually 2 other ways that these problems could end up working out for us. So those are the ones that I really want to talk about today and focus on. Here's our next example. In this case, again, the box is representing what we don't know. It's the x. We don't know what value goes in there yet. So I end up with x plus 3 equals x plus 5. If I was to go ahead and try and solve this problem, I would want to move all the x's to one side. So since I don't have one that's smaller, let's go ahead and move them to the left. So I will subtract the x from the right side and subtract x over here. Whatever I do on one side, I must do on the other. So 1x minus 1x leaves me with 0 x's, and 1x minus 1x leaves me with 0 x's. And so I actually end up with 3 equals 5. Well, 3 equals 5 is not true. That's always going to be unequal. So what happened here with this problem is that they gave us an unbalanced problem to begin with. There's no way that 3 is going to equal 5. There's no number or value I could put in for x that's going to make 3 equal to 5. They are inherently unbalanced. So this was a faulty equation to begin with, and there is actually no solution for this. And that's what we would say. We would say there is no solution for this type of a problem. There's no number x could possibly be that would make 3 equal to 5. So this is a special solution. It's where there is no solution. Okay, so our next type of problem is our second special solution. Let's take a look at what this one looks like. So again, I don't know what x is. So if I write an equation that matches my balance beam, I end up with x plus 4 equals x plus 4. Well, if I go ahead and solve this the normal way that I would, again, I don't have an x that's smaller to move, so let's just move them to the left. I'll subtract x from here and from here as well. And so that actually leaves me with, well, I've got 0. Uh-oh, my problem went away. There we go. I've got 0 plus 4 is equal to 0 plus 4. Well, that means I've got 4 equals 4. Well, that seems simple enough. 4 is equal to 4. It's always going to be equal to 4. So what this actually means is that, again, I have an equation that is balanced, but it's balanced all the time. And you can kind of see from our original setup of the problem, it already looks like it's balanced. Like we don't even need to do any work to make it balanced. And what this means is that this is a problem that it doesn't matter what value we put in for x, it's going to be the same no matter what. And so we say that this one has infinite solutions. That's our second type of special solution, where the equation will always be balanced and has infinite solutions. I could put 1 in for x. 1 plus 4 equals 1 plus 4. Works. I could put 10 in for x. 10 plus 4 equals 10 plus 4. It works all the time. So it doesn't matter what value we put in for x, every value will work. Okay? So these are my two special solutions. I have one that's no solution, and I have one that's infinite solutions. And there's a very special circumstance that happens when we end up getting a special solution. And you may notice when we went through and we solved these, in this middle step right here, we ended up in both problems with no x's. And that's our key that we're going to get a special solution. When we're going through our normal solving steps, our variables end up zeroing out. We don't have any more variables in our final solution statement. And that means I have a special solution situation. Okay, so let's practice a couple of these. Here's our first one, and we can see, again, we're going to use all of our normal solving steps like we would for any other kind of problem. So the first thing we want to do is simplify. I'm looking here on the left, and I am seeing that I have a couple of like terms. I've got 6n and negative 5n that I could simplify. So 6 minus 5 gives me 1n, still have plus 12, and that is equal to 12 plus n. So then my next step would be to move all the n's to one side of the equals. Let's go ahead and move them to the left. So I subtract n here, 1n, and I subtract 1n over here. Well, how many n's do I end up with? I end up with no n's. So that's our key. We're definitely going to have a special solution because I have no variables left over, right? If I end up with 0 variables, I'll have a special solution. So in this case, we want to see if this is going to always be balanced or if it's inherently unbalanced. So is 12 equal to 12? I mean, all the time, right? So this is a true statement. Since it is true all the time, no matter what, it doesn't matter what value we're going to put in for n, it's always going to be true. So this one is infinite solutions. Okay. We have infinite solutions. Any value will work for n, and this will always be a balanced equation. Okay, let's go ahead and take a look at another one. So again, we want to make sure that we are using our same solving steps we would always use. I'm going through and I'm making sure that my equation is simplified first. So I'll take this negative 3 and distribute it in. So negative 3 times 6 gives me negative 18. And negative 3 times negative 4 gives me positive 12, and that is equal to 9 minus 18m. We want to make sure that we're moving all our variables to one side of the equals, so let's go ahead and move them to the left. That means that I will add the 18 and add the 18. So now I have 12 is equal to 9 because negative 18 plus 18 is 0. Negative 18 plus 18 is 0. So my final statement is not true. This is inherently unbalanced. They gave me a faulty equation to begin with, and so this one is no solution. And that's what we should state as our answer, no solution. It's not a working equation. There's no way that I can have a value for m that will make it true. Okay, let's go ahead and take a look at one more. This is a very important example, and our last one. So here we go. Again, we start with our normal solving process. We're going to go ahead and distribute that negative 7 to make sure that our problem is simplified before we start to solve. Negative 7 times 1 is negative 7. Negative 7 times negative 8 will give me positive 56. And that is equal to negative 7 minus 6n. Now I want to go ahead and move all my variables to one side. Since I see I have smaller n's on the right, I'm going to go ahead and move those. So since it's subtracting, I will add as the inverse. And over here I will add. So now I have a negative 7 plus 62n equals negative 7. So since I moved all my letters to the left side, I need to make sure I take my numbers and move them to the right side. So I will add the 7 to each side. I'm going to rewrite up here so I have space for my last step. That gives me 62n is equal to 0. So the important part here is that I still have n's, and I can still do one more solving step to figure out what n is equal to. I will divide by 62. So I'm dividing 0 into 62 pieces of nothing. And so n is equal to 0. So the important distinction here is that I still have n's in my final step. They didn't disappear like they do for our special solutions. They're just equal to 0. And n can be equal to 0. 0 is a number that works for equations just as well as any other number. Okay, so it's important to keep this one separate from our special solutions where all our variables disappear. Okay, and that's all there is to it.